This lecture is going to look at the concept of the energy grade line and the hydraulic grade line. Now, before we get to definitions of those two things, we want to take a look at what happens when we have flow through a pipe and the diameter of the pipe changes. So this little illustration here, the flow is from left to right. So we're going from a large diameter down to a small diameter through this transition piece here, this contraction. Now we need to recall what Bernoulli's equation looks like. So Bernoulli's equation tells us that P over rho g plus V squared over 2g plus Z is a constant. Now you remember in the last lecture we were writing Bernoulli's equation between 2 points, point 1 and point 2, and you don't see those subscripts on the properties in this equation. Well, realize that there's streamlines heading down this pipe, and we can choose any 2 points along those streamlines to write Bernoulli's equation between. So another way of saying that all of this stuff at point 1 has to equal all of this stuff at point 2 is just to say that the sum of these three things as we move down the pipe has to remain constant. In any particular application, we might choose to put point 1 and point 2 at convenient locations, but it follows that the sum of those three things is a constant along the pipe. So what we're going to do is plot various parts of this as a function of distance along the pipe. Now realize this form of Bernoulli's equation is the so-called head form, where we've divided through by rho g, so the dimensions of each of these terms is length, or if we think of it in terms of units, meters. So the vertical axis of this plot is going to be head, which is what we call those terms when they're written in those units. And the horizontal axis here is going to be position along the pipe, so just along this axis here. Well, the very first thing that we'll put on this plot is a line of the total head. So the sum of these three things is constant, so the sum of those three, the total head, is just a horizontal line. Now what we want to do is think about how do the various parts of this thing change as we go down this pipe. So just to simplify this discussion a little bit, we're going to say that this is a horizontal pipe. So there's no change in elevation, so that particular term is not at play here. So what we're going to be looking at is changes in these two terms. But a very important thing to remember is that no matter what happens as we go down this pipe, the sum of those two things has to stay constant. And remember, that's conservation of energy. Well, the first thing I want you to think about is what happens as we go through this contraction to the velocity of the fluid. Now remember, we're talking about incompressible fluids here. So when the diameter reduces like this, the velocity has to increase. Remember, if we were to measure the mass flow rate across that line and the mass flow rate across that line, they have to be the same. So if the area goes down, the velocity has to go up. So hopefully you can see that the velocity here is much higher than it is there. So if we were to just plot velocity with position, we would see it increasing as we go through this contraction. Now what we want to plot on here though is the pressure versus position, or more specifically this static head, P over rho g. We want to plot that versus position along this pipe. Well, realize that if the velocity is going up, the pressure has to go down because those two things need to remain constant. So that's the key thing, is to understand that Bernoulli's equation is at play here. So any increase in velocity must be accompanied by a decrease in pressure. And notice the pressure change is quite dramatic because of this squared here. If the velocity were to double, the pressure would have to go down by a factor of 4. So quite large pressure changes accompanying modest velocity changes because of this square on the velocity in the kinetic energy term. So when we plot P over rho g as a function of position, we see that as we encounter this contraction, it dips down to a new level down here. So this is the piezometric head that I've plotted here. Now remember, piezometric head is the sum of these two things. but the Z is not changing in this illustration. So really we're talking about the pressure here. It's changes in pressure that are giving us this piezometric head plot on here. Now, this is a little bit counterintuitive for some folks because they think, well, the fluid is coming along here and it goes into a smaller pipe, so it's more crowded in there. The pressure must get higher because we're jamming that liquid into a small pipe. But that's not what's going on here. The velocity has to increase if the density is going to stay the same. And if the velocity goes up, this fluid has more kinetic energy. Therefore, the enthalpy has to go down because that's where that energy came from. The thing that is accelerating this fluid, making it go faster, is a higher pressure here and a lower pressure there. That's what accelerates the fluid, is that decrease in pressure. So get used to that fact. As the velocity goes up, the pressure goes down. Now exactly the opposite would happen here if we had the small pipe over here and the big pipe over here. So if we were flowing from small to big, the velocity would go down and the pressure would go up. So this is our plot of piezometric head. Now the other thing that we can show on this particular plot is that the difference between these two lines is the kinetic head, because that's this term. So the difference between the total and the piezometric head is the kinetic head. So certainly it makes sense that this is bigger here because the velocity is bigger. So increasing velocity, increasing kinetic head, decreasing piezometric head. So these lines that we've been plotting here have specific names. The first one that plots the total head as a function of position is called the energy grade line. Now remember, the word energy is being used here because that's essentially the total energy in the flow. We'll see why it's called a grade line in a little while, so don't worry about that part of it just yet. This is a plot of total energy, so it's called the energy grade line. The plot of the piezometric head as a function of position along the pipe is called the hydraulic grade line. Now remember, that's only a portion of the total energy. That is the sum of the enthalpy, P over rho g term, expressed as a head, and the elevation. So even if we were looking at piping systems here that were going up or down a slope, hydraulic grade line is still the sum of P over rho g plus Z. So these are the two grade lines that are the topic of this particular video. Now, remember, one of the features of Bernoulli's equation is that it's for frictionless flow, so no frictional losses of any kind. Well, it turns out that for piping systems, like we're going to be looking at in this module of the course, that is not a very realistic assumption at all. So although we've been looking at the true Bernoulli's equation here for the last couple of lectures, in order to use that for piping systems, we really need to make a modification to it. And what this amounts to is going back and removing one of the assumptions that we made. So we assumed that there were no viscous forces or no effects of viscosity. So we need to now bring back in these frictional effects. So the way that we do that is we add a so-called head loss term to Bernoulli's equation, and it's there to account for frictional effects. So we'll see what Bernoulli's equation looks like with losses added to it. So here's what it looks like. And again, it's expressed here in head form. Well, all of this stuff is the Bernoulli's equation that we've seen so far. So the sum of those three terms at point 1 equals the sum of exactly the same three terms at point 2. So if we have a frictionless flow, no effects of friction at all, then that's the form of Bernoulli's equation that we would use. Now, when there are frictional effects, and there is certainly frictional effects in a pipe flow, it's a very important term, some of the energy in these three terms is lost. Now, of course, energy doesn't just disappear. It goes somewhere, and the place it goes is it's dissipated as heat. But the way that it's accounted for in Bernoulli's equation is by adding this head loss term. So H sub L is our head loss term. And remember, we are adding that to the right-hand side of the equation. Now, does that make sense? Well, yes, it does. Remember, point 1 is upstream, and point 2 is some point downstream. So because we're adding this positive number to the right-hand side, it means that this must be smaller than this. So some part of the total energy has been lost or has been dissipated into heat. And this head loss term tells us how much. So as we go down a piping system, the sum of these three terms doesn't actually stay constant. Because of this head loss term, it continually decreases and decreases and decreases. The next video that we're going to look at, we're going to be looking at this head loss term in a lot of detail. Now, I'll just quickly introduce where these head losses are coming from here. So there are two sources of head losses. Now, they're really the same thing. They're both frictional effects, but the way that the head loss is calculated is by considering these two separate effects. The first one is pipe friction, and this is typically the most important one. So this is the friction on the walls of the pipe, the inside walls of the pipe as our fluid flows down it. And there is a way to calculate the head loss due to pipe friction, which I've given here. I'm not going to go into this equation at all right now, actually, because the entire next lecture is going to be talking about that. But this gives one part of this head loss term, which is called the frictional head losses. So H sub F is the head losses due to pipe friction. Now the other part of this is so-called minor losses. And those are losses, they're still frictional losses, but they're losses that occur in fittings. So elbows or contractions like the one we saw in the illustration earlier in this video, or T's or valves or all sorts of fittings that there might be in the piping system. So these are frictional losses in those fittings. And that's calculated in much the same way as the pipe friction. There's a little bit of a difference here that we'll be talking about in the next video. So the sum of these two things, the pipe friction and the minor losses, are the head losses. Now, what we're interested in this video is not how to calculate those things just yet, but what effect do they have on the energy grade line and the hydraulic grade line. So we're going back and revisiting this sketch. So the energy grade line that we talked about earlier was a perfectly horizontal line. So I've labeled this energy grade line ideal. Ideal meaning no frictional effects whatsoever. So ideal flow, no friction. Well, the actual energy grade line, remember what energy grade line is. P over rho g plus v squared over 2g plus z, the sum of those three terms. Well, due to frictional losses, as we go down the pipeline, the sum of those terms is decreasing. So our energy grade line would actually look like this. And the difference between those two lines would be the head losses. So the further we go downstream, the more head losses have accumulated. Now, notice a few features of this actual energy grade line here. It's a constant slope back here because the frictional losses in here are constant. There's nothing different here or here. So we would see a constant slope in that energy grade line. Then we come to this fitting here, which is a contraction, which there'll be some minor losses associated with. So we would probably see a sort of a sudden drop in the energy grade line there, meaning there's some losses associated with that particular fitting. Now we're into the smaller part of the pipe, so the velocities are higher there, and the friction is actually more because of the higher velocity. So you'll notice the slope of the energy grade line here is larger than it is there. So those are the features that are important here. A particular slope here, a drop due to the minor loss in the fitting, and then a higher slope here. Now notice one feature of the energy grade line is it's always going down. You will never see an energy grade line increasing. If you see the energy grade line increasing, something's wrong because that means there's being energy added into the fluid there somehow. And for simple systems like we're looking at so far, that's not possible. There's no pumps in these systems yet, so the energy grade line cannot go up. There's no energy input. So this also is where the term grade line comes in. This is why it's called an energy grade line, because it has a grade, it has a slope. As we go down the pipe, the grade line decreases and decreases. And the higher that slope is, the more the energy losses are. Now, we can also put the actual hydraulic grade line on this. Now, realize that the ideal version of this that we saw a couple of slides ago, the distance between the energy grade line and the hydraulic grade line is the kinetic head, v squared over 2g. Well, that's still true here. The distance between these two lines is going to be exactly the same as it was for the ideal case, because the velocities here are going to be the same. Okay, so the hydraulic grade line also becomes sloped down at the same slope, in these regions at least, the same slope as the energy grade line, because the distance between here and there has to be the same, because there's no velocity change there, because there's no diameter change. So the distance between these lines is actually the same as it was in the previous one. But because the energy grade line is sloped, the hydraulic grade line also has to be sloped. So these two lines are what would happen in a real piping system. Now, it might not be quite as dramatic a slope as we're seeing here. This is just a little sketch that I've made, but the key feature is the energy grade line would be sloping down. Now, realize in this particular example that I've given here, the hydraulic grade line is also sloping down. Hydraulic grade lines can actually increase. So the energy grade line always has to decrease, but a hydraulic grade line could increase. Imagine if this pipe were flipped around, so we were going from a small pipe to a large pipe. Well, as we go from small to large, the velocity goes down, so the pressure goes up. So it is possible for this hydraulic grade line to increase rather than decrease, but not for this particular geometry here. In one of the labs that you're going to do quite soon, you're going to make measurements of these energy grade lines, both the energy grade line and the hydraulic grade line, for a little bit more complicated geometry than this. And you will see your hydraulic grade line both decreasing and increasing, and you should see your energy grade line just going down and not increasing. But we'll leave that to the lab for you to see for sure. So that's a brief introduction to energy grade lines and hydraulic grade lines. In the next video, we're going to look at this head loss term in detail and learn how to calculate the frictional and minor losses in a piping system. So we'll see you in the next video. Thanks for watching.